Okay, we're going to start this lesson today. This entire chapter, chapter 4, that we're going to be working on, is all about two-dimensional motion. Two-dimensional. What do I mean by that as opposed to one-dimensional motion? Last test that you just took was all one-dimensional motion. And now we're going to work on two-dimensional. So what is one-dimensional motion, right? We just took a test on it. What do we mean when we say one-dimensional motion? Good. So either up and down or left and right. That's the only dimensions we have in one dimension. Now, out of the page and into the page is actually another one-dimensional option, right? So when we think about the world being three dimensions, really, three dimensions is left or right, up and down, out of the page, into the page. That's the z-axis almost, which you haven't really seen in math much. We're going to be focusing now on x direction and y direction at the same time. In the last test, it was either, as Joe said, only moving in one direction or the other. It was either going horizontally as a car moves, or vertically as an object in free fall or an object being launched moves. But what if we go to that example where the soccer goalie or the football punter kicks the ball downfield? He or she does not kick in only one dimension. He or she kicks at an angle so that it follows some sort of parabolic path, right? And we call it, in physics, we're going to use the phrase projectile later. So in this lesson, we're going to get into the basics and the fundamentals you'll need for the math behind this actual topic. So 4.1 and 4.2 we'll do together as vectors. When we get to 4.4, we'll spend about 3 or 4 lessons full periods on that topic, because it's not a tough topic. But remember how with the vertical motion problems, there were a couple types? You could have a free fall, you could have on the way up, on the way down, how we broke it into those pieces. The same thing applies for two-dimensional motion that we're going to see. But this here, this is the math needed for it. Without this lesson today, you're going to be lost in 4.4. So this is like the fundamental or the building block that we would use to help us with 4.4. Yeah? Good? Okay. All right. So we're going to first define our vector. So let's define a vector. And a vector, it's given here, is a physical quantity that has both magnitude and direction. Magnitude and direction. In the last chapter, we had several quantities, physical quantities, whose direction mattered, and several whose direction didn't matter. Which of those physical, you can use in terms of variables, which of those variables, physical quantities that we've been studying, involved direction, where the direction mattered? Give me one. Velocity. Let's jot these down on the right side. These are vectors that we're talking about, where direction matters. Velocity, the direction matters. And we know that, as Helen said, because if I move to the right, velocity is positive. If I move to the left, velocity is negative. So the direction clearly changes my velocity. What else did the direction matter? Displacement. Very good. That's the second one. So our vector examples, we can write over here, are velocity, displacement, and one more that is not obvious. It's not obvious. What is it? Acceleration. Good, both of you guys at the same time. Acceleration. Acceleration. And that one is not as obvious because we have not dealt with positive acceleration upward. We've only dealt with gravity, where it's always negative. But if you recall the examples like, hey, a car accelerates from rest to 60 miles an hour, that's positive acceleration. But just like the multiple choice example on the test yesterday, what if you're moving positively? How can you slow down? What kind of acceleration must occur? Negative. Very good. Negative acceleration. So acceleration direction matters also. So velocity, displacement, and acceleration. What quantities, variables, quantities have we looked at that do not involve direction? Do not involve any direction at all. The direction didn't matter if we're calculating these quantities. Nick, what do you think? Speed was one of them. So let's jot that down on this side. We're going to call these in a minute scalars. When they're not a vector, it's a vector or a scalar. S-C-A-L-A-R. One more? Time is another one. Good. Time, the direction didn't matter. So speed, time, and I can think of one more. Distance. Well done, Helen. Distance. If I walk 5 steps right, and then I walk 5 steps back, I have walked 10 steps in distance. But my displacement is 0, because it's a positive 5 and then a negative 5 for displacement, and those add up to 0. But for distance, it's a positive 5, another positive 5, and that gives me 10 for distance. So distance, the direction does not matter. Speed, the direction does not matter. So believe it or not, in the last chapter, you already learned about vectors without realizing. You learned about vectors. You learned about physical quantities, for example, velocity, displacement, acceleration, where the direction mattered. Now, that's one piece of this whole puzzle we're going to put together. The second part, the symbol for a vector is usually an arrow. And it's very easy to draw vectors if you have two components. When I was in college, this piece over here, like this is like the head of your body and like your tail. They call a tail the back of it, like your feet. Think about your physical person as a vector. If I could lean like this, I could lean like this. My head is like the front of the arrow, and my feet are the back of the arrow. But in physics, we call this the tail. And you can call that the head or tip. Either one is fine. When I was in college, we called it tip-to-tail method when you came to summing these things. Your book calls it head instead of tip. It doesn't make a difference, they're interchangeable. But the idea of a vector is that it has a direction that it's going toward. And we will physically show that as a representation on a graph in a little while. Okay, let's keep going. Let's take a look at adding vectors together. So if I had two lengths, let's say I walked from here to here, and then I walked from here to here. Well, that's the same thing as just doing this, right? Same thing as just going from A to B instead of that longer path. If I could cut through Central Park like this, instead of going up maybe along Central Park West, and then cutting across the 86 Traverse, maybe I can enter down here at like 75th, and just go northeast the whole time and cut across. So with vector addition, we simply do the same thing. So we take our first vector, and put it right here. So here's our first vector. We literally write it here. We then take the tail of the second vector and put it right up against the tip of the first vector. And as a result, this is the second vector coming from the first one. So the end, or the tip of the first vector, is the tail of the second vector. Very much like velocity we talked about. Remember those problems where it's launched straight up? The final velocity on the way up could also be called the initial velocity on the way down. We thought about the problem as breaking it up into two pieces. Well, the same thing here. So again, this person can walk from A to B and then from B to C. But they could also just walk right from A to C. And we call this right here the resultant vector. A capital R with an arrow over it. Whenever we sum vectors together and find what we call like the shortest root, in this case is in red, it's called the resultant vector. Today we're going to really focus on doing this all by drawing things out. We call a graphical solution. That's what we're going to focus on today. Tomorrow, in the other lesson, we're going to get to the algebra behind it. Tomorrow or the next day, whenever I see you guys in the next class. Okay? So let's continue with this concept, graphical analysis. So let's take a look at this diagram. There's a lot going on in this diagram. I really want you to focus on the directions in the order you're given. So if I want to add vector A and B together, step 1 says draw vector A to scale. So I literally draw vector A right here. Step 2 says draw vector B to scale, starting at the end of vector A. So I start with vector B and I draw it all the way up there. And step 3 is draw a line from the beginning to the end. And again, we call this the resultant vector. What's interesting to note, though, is that these are really just a bunch of triangles. There's a lot of triangles happening here. It's tough to see them if we don't draw them. So we're going to go ahead and draw them as a superimposition, or a superposition on top. So if I think of R as a hypotenuse, look at R and think of that as a hypotenuse. Draw down a vertical from the end of R until you get to the point where it lines up with the bottom of the starting point, and then connect this horizontally. You guys have a feature on Notability to make a straight line. Do your best. Use that. I'm doing my best up here to make these perfectly straight lines. So in green, what we have are the legs of the right triangle that makes up vector R. Again, vector R, your resultant, can always be thought, or all vectors can be thought of as a hypotenuse. When you have a hypotenuse, you can draw on the legs. Think of A now. Think of vector A as a hypotenuse and draw vector A's triangle. The same way we drew vector R's, right? We took the end or the tail and the beginning or the tip there and connected them with perfect lines like that. Let's do the same thing for this one to make its triangle, and let's do the same thing for vector B to make a vector B triangle. So I want to see a triangle for each of these three vectors. I'll use colors, the same colors that are here. That line is not drawn at the correct angle. Let me just make this better, Helen. All right. I'm kind of covering the green line, not on purpose. The green line is behind it still. So look at my triangle for vector A. I want you to always be drawing right triangles for these. We're going to utilize these a lot. You can put a little right angle symbol if you want, but we know that they're right angles because we're drawing right triangles. And then for vector B, the same thing. You'll notice here, you go back to geometry from last year, there was something called segment addition postulate. Sounds fancy, it's not. It's like saying, hey, you know what? You're going to walk 5 meters, and then you'll walk another 4 meters. What's the total you're going to walk? 9 meters. Literally addition, that's all it is. Same thing here. And what I'm going to do here is I'm going to designate with variables what's going on. So this overall length here in green, we'll call that Rx. And the overall length here in green, or height in green, we'll call that Ry. Let's give those labels. So the triangle we drew for the resultant R, we'll call Rx, and we'll call that Ry. In red, that triangle could be denoted as AX and AY. It's tough to see it. That's an AX right there, and that's an AY right here. Call those AX and AY. And then in blue, the same thing. BX and BY. And the statement that you should be able to visualize or understand is that if you add AX and BX together, what is that going to be equal to in this case? RX. RX. The sum of the pieces equal the whole. The sum of the pieces equal the whole. So AX plus BX is going to equal RX. And therefore, the next statement I can write would be, what could the other statement be? We've taken care of the X part. Kim? Yeah. Okay. So again, what we're recognizing is that if we want to figure something out, we can break things into pieces. We call them in physics components. If I said, you're missing a component that you need to build this desk, that's a pretty big problem, right? Maybe you're missing a leg and you can't build the desk. A component is a piece of it. So we break our vectors A, B, and R into their components. And if I'm able to determine AX, which I can graphically, literally look, 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes, 9 grid lines or 9 grid spaces. BX is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 9, this is 10. I said 9 the first time, right? 9 and 10 gives us a total length for Rx of 19. So the graphical approach to figuring out what R is not that hard. Now, I'm not actually given R though. I'm given Rx and Ry. Right? Again, I can find Rx and I can find Ry from these two equations. From adding these pieces together to give me the whole. Add these pieces together to give me the whole. And I showed that in the other class a little bit better like this. Let me try and do this well. It's tough with the pointer. So this distance right here, tell me it's not going to let me do, there we go. This AY, see the 2 dots I'm using here on the board? This distance AY right here could technically be slid over to here. That's the same height as AY right there where I'm pointing to, between those two dots themselves. And I could take that AY plus that BY, and that's going to equal this entire length, which we're calling RY from top to bottom. What can I use to find out the value of R? What can I use to find R? Kim? Yeah, awesome. Pythagorean theorem. Okay, so a lot of geometry, a lot of stuff with triangles, and even in the other class in a minute, we're going to see like parallel lines with the transversal. Remember all that stuff that showed up? It will play a role. You're not going to have to know the vocab, but you have to know which angles equal each other and which are alternate interiors, so you know if they're equal. So we're noticing that we'll use a little bit of trig here, but we have this formula now. And that's Pythagorean theorem. That's all it is. A squared, which is Rx squared, plus B squared, which is Ry squared, equals the hypotenuse squared, and the hypotenuse is denoted as R. Guys, we need to make sure we're all focused right now, not doing other stuff. Everybody better be focused. This R right here, again, is our hypotenuse, and these are the legs of the triangle that we're trying to figure out. I want to do an example so we can see how this works and a little bit of numbers, not just variables and letters everywhere. So let's go to the example here. Let's take a quick minute to read through this. Do you want to read it for us, nice and loud, has a deep voice or a loud voice? Elias, go ahead.
The person starts to walk and travels 0.4 miles north before stopping for the sun. Then the person walks 0.2 miles east and waits to read a book in the park for a while. After this, the person then travels 0.7 miles south and another 0.6 miles east, rapidly determining the person's final location with respect to the sun.
So we're going to use this grid here to actually draw the path in which this person is traveling with all vectors. All vectors. I made this one easy. For today, I made it pretty easy because the vectors are either up and down or left or right. North, south, east, or west. We're going to talk about vector components or vectors at angles soon, and we're going to see how that plays a role as well. But for today, we're going to do the easier version. Because I know this person is going to be traveling north, then east, then south, and then east, it means they're going to do something like this, right? They're going to go north, somewhere east, somewhere south, and then somewhere east. So I know we're generally going to be traveling east. And I know I'm going to go north and south. So let me start somewhere in the middle, but on the left side. So you pick a box to start in. Pick a grid line, maybe here, or here, or here. You pick whichever intersection you want, somewhere in this region. I'm going to do the same thing. It doesn't have to be the same as mine. I'm going to make that my starting point. Again, it doesn't have to be the same, and I don't want you to pick the same if you haven't. Now, that's your starting point. And just go in order of the directions. This person travels 0.4 miles north. So what do I have to make? I have to make the assumption that one box is equal to 0.1 miles. I need some sort of a scale so I know what I'm moving. And again, I'm going 0.4 miles north. That's 1, 2, 3, 4, and that's my vector for that. And again, yours may look different because you started somewhere else and not exactly where I started. But the idea behind this is that you're going 4 boxes up, 4 grid lines up. After that, what does the person do? What do they do next, Alon? Yeah, 0.2 miles east. So is that going to be to the right or the left? Yeah, east is to the right. And let's make sure that we're clear on this. With any diagram that we're going to use in this class, we're always going to assume the following, right? There's our compass in the top right, or south, east, west. Anyhow, yes, we move to the right 2 boxes. So let's go ahead and do that. And I'm using a color coding system based on what I'm underlining. So later you can see this, or you can do the same if you'd like. Might help you when you're studying, right? And then 0.7 miles south. What do I do for that? 0.7 south. Kev? Down 7. So here's down 4, and then 3 more. Puts me there. I went back down 4, the same 4 that we went up a little while ago, and then 3 more. 4 and the 3 makes 7. And then the last leg of the trip, 0.6 miles east. So naturally I go. Yeah. Okay, 6 boxes or units or grid lines to the right. What path second and the blue path first? What if I went 0.2 east, then 0.4 north, then 0.7, and then 0.6? Yeah, why is that? Why can't I do that? What law of math do we know when we can switch the order in which we're doing an operation? Yeah, commutative. Very good. Commutative. It is the law of commutative for addition. I can change the order in which I'm adding vectors. We're going to see that in a little while as an example. But I want you to recognize it with this graph because it's very obvious. If instead of starting here and going north, what if we went south? Okay, go south, set 0.7 miles. Then maybe you would take the north route 0.4. Then the east route 0.2. And then the other east route 0.6. Hey, you still end up at the same point. So the order in which we take this path does not matter. Now, if this is your path in the city, and you're like, hey, I'm going to get lunch, I'm going to stop in the park to read a book, I'm going to the store to buy some new clothes, and then I'm going back home, or I'm going home, and this was maybe Loyola right here, well, maybe you walked up north to like 90th, over, and back down to 70-something. I'm just thinking this is 83rd, right? Down to 70-something, and over to 70-something and East End, or York, or whatever. But the concept is that the path taken doesn't matter if you don't care about those stops along the way. So if I want to go from beginning to end now, let's connect that from beginning to end. And you have a straight line feature on your Notability program. Please use it. Okay, there's my straight line from beginning to end. So if I wanted to not take this longer path, but still end up at the same point, and I had like a little hovercraft maybe. Have you ever seen the Jetsons, or is that way too old?
Yeah.
You know, have you heard of the Jetsons? They can fly? Okay. In the cartoon, the Jetsons, they had a little flying car. So imagine you had a little flying car, and you were literally trying to get from school home as quick as possible. Just one way home, right? You can take a little flying car, and you come right across the city, and get to your house that way. And we called that the displacement. Remember earlier we called that displacement? So this is really the same thing as the resultant of a bunch of vectors added together. Just like the last slide, we added vector A and vector B together to get an overall distance from A to B, or overall displacement really from A to B. Same thing here. So the black line represents the overall resultant vector in this diagram. How am I going to find its length? How am I going to find the length of the R vector, Kev?
You could just draw the line down, make form a triangle,
Yeah. Very good, Kev. So go ahead and draw your triangles again. Take a look at the triangle I just drew. I've got the vertical component. I've got the horizontal component. Remember the word component. I'm going to keep using it now that we know it. The vertical part and the horizontal. If I follow the black dashed path, don't I end up in the same spot? Sure I do. Sure I do. So the goal is to figure out what is your resultant vector, and then take that vector and figure out its components. Got it? Okay. Point 3 and point 8. If you're not sure where I got that, what did I do? Count the boxes. Very good. Literally counting the boxes. I could also figure it out another way. Who could really see how else do we get the point 3 and the point 8? Without the boxes. Make believe I use the boxes now because I'm trying to teach it this way first. Careful. That means you didn't go up the right or down the right way. Count your boxes up and down for the other paths. Joe, what do you think?
7 minus 4, which is basically what you're doing.
And then this piece, Joe?
6.6 plus 0.2.
Yeah, take a look. Listen to Joe one more time. As he says it, I'm going to point. Start with the left or right, Joe.
Okay, so that's 0.2, then that's 0.6, to be 0.8.
Then?
And then that's 0.4 up,
And then?
and then 0.7 down, and then so if you like subtract it.
Because the 0.7 down is like a negative 0.7, right? So this is a 0.4 up. So the 4 that we went up, we lost that 4 coming back down, and then went an additional 3 or 0.3 miles to make this a full path of 0.7. So this net result is this guy subtracted from this guy, actually. So when you're doing it graphically, inspection helps by looking. When we get to doing this algebraically in the next lesson, negative, positive signs will definitely matter, as you can see. This would be a positive 0.4. This would be a negative 0.7. We might even label this as a negative 0.3 later on. And we'll see how that plays a role in the algebraic approach. For the graphical, I'm not too worried about signs right now. The goal, though, again, is to find out what r is. So we have, again, rx squared plus ry squared equals r squared. This is 0.8. This is 0.3. And our goal is to figure out r. 0.8 squared is 0.64. 0.3 squared is 0.09. And that equals r squared. If I want to get r by itself, what do I do to get rid of a square? Square root it. And what's the square root of 0.73? Approximately it's going to be greater. I know when you take a square root of a decimal, it gets bigger. What do we got? We have no calculators today, do we? You're just guessing numbers right now. It's 0.854. Come on. Check on your calculator. You guys all have calculators. Let's use them. Okay? Remember, when you take a square root of a number, a decimal, the answer always gets bigger. This happens to be a decimal, right? How do I know that this answer is reasonable, Lon? You shook your head like you were confused, so I'm asking you. How do I know that this answer is reasonable when I look at my triangle in black? Sure, I can try and plug it in, check it. Yes, reasonable. I don't want to do all that work. When I'm doing a sensibility check, it needs to be something quick that I can physically see that makes sense. What part of the triangle is R? What part of it do you call it? And the hypotenuse is always the biggest leg. That's it. Okay, so again, the hypotenuse is definitely the biggest leg of any right triangle. So as a result, this answer has to be bigger than the two we started with. It's got to. So whenever you have your components and you sum their squares together, the answer you get will always be greater. Now, that was the easy part. The harder part for the graphical look is the angle. And it's not difficult at all. But I'm going to be drawing a bunch of lines and it might be a little bit confusing if you, for a second, start texting somebody and you're not looking up and you're not paying attention, right? So if you miss it for a second, you're going to be lost. So what we do here is the following. Whenever we want to measure our angle, we take the starting point and put a dashed horizontal line through the starting point. So let's start with that, please. Put a dashed horizontal line through the starting point. That's step one. Now, the angle, we're going to probably want to write this on the side. The angle measurement for vectors is always the angle. The angle measurement for vectors is always the angle between the resultant and the nearest horizontal axis. The angle that we'll use to represent vectors is always the angle between the resultant and the nearest horizontal axis. Why do I say nearest? Let me explain. So in my diagram, if it's clear what I'm talking about, the angle that we're referring to, I'll use red here, is this piece, oops, that's not correct, I want to use a pen, is this piece right here. That's the angle that I'm referring to. Physically, this piece right here that I'm sweeping out with my hand. That's the angle. The reason I say the nearest horizontal axis is because, take a look, I can technically go from the vector all the way around to this horizontal axis. And these are supplements of each other. If this is 20, this is 160, and therefore the whole thing is 180, and back to straight lines and angles and geometry. So again, we're always going from the vector to the nearest x-axis, or the nearest horizontal axis, not the one over here. And the horizontal axis that I'm referring to is always the horizontal axis that goes through the starting point. This is always going to be drawn through the starting point. Always, always, always. Now, how do I find theta becomes the question. And in the other class, I had 2 suggestions. You want to give me a suggestion to start? You have an idea?
Using tangent cosine.
Yeah, we're going to use trig to do it. Very good. We're going to use trig. Now, what somebody in the other class noticed, which was very intuitive of him, in this case him, was that this angle theta in red is the same as this angle right here. These are alternate interior angles of parallel lines cut by a transversal. Again, think back to geometry last year. I don't care about the vocab right now, I really don't. I'm using the vocab because it's correct. But if you can see it, that's fine. Here are my parallel lines. Take a look. Those are my parallel lines. And there's my transversal. The angles that are alternate interior, alternate meaning on the opposite side of the transversal, and on the inside of the parallel lines, interior, inside, alternating, these are always the same angle. So the student in the last section suggested, why don't we just find this angle right here by using opposite and adjacent, and then we could say it's the same thing. And that absolutely works, 100%. I just want to show you that we could also just complete the rectangle by putting a dashed line right here. Complete the rectangle real quick. And now we have another right triangle on this side. Notice the change in the pitch of the siren? As it approaches you, it's a high pitch. As it goes away, it's a low pitch. We'll explain that later in the share. It's called the Doppler effect. The Doppler effect. It's really interesting, actually. It has to do with sound waves compressing. So if we look, we see we have a rectangle. And a rectangle is really 2 triangles smushed together. That's all it is. We take a rectangle and cut it diagonally, we get 2 right triangles. So what I'm going to do, and again, you could use the other triangle, I'm going to rewrite the lengths. I know this is 0.3, and I know that this length up here was 0.8. It's a rectangle, so the lengths are the same, the widths are the same. So I could use either of these triangles, but because theta, in this case, theta is in the upper triangle of the 2 triangles, the upper one, I'm going to use the red lengths, even though they're the same, they're identical. Now, I'm going to draw that triangle over here so we can all see it. Okay, so I'm literally extracting this triangle that I'm highlighting right now. I'm extracting this triangle right here, and I'm drawing it over here on the side. How do I find out what theta is? This is right off your summer packet. Literally straight out of your summer packet. How do I find theta? Warsaw. Careful, that's the hypotenuse.
Sorry.
And we did that, right?
Yeah.
We did that here to find the hypotenuse. What do you think we should use to figure out angles?
So angles of... Can we assume that one of them is right?
We absolutely can. Very good, Nick.
So that, what we do is...
Which one is it going to be, Nick?
It's going to be, well, it's going to be 45 or 40. No. Oh, okay, so you want to find the, from the right angles perspective, that would be the...
Is your angle, right?
Yeah, sorry.
And this, and the triangle is, what do we call this side?
So it'd be adjacent over hypotenuse. No, sorry.
That's okay. That's all right. Get help, Mort. Help him out. Why tangent, Mort? Take a look. This is hypotenuse, right? And we found the hypotenuse earlier. And you might be saying, Mr. Howell, why aren't you using the hypotenuse, right? Why didn't I label the value on the diagram here of 0.854? Well, in case we made a mistake in our math and this answer is wrong, we don't want to make another mistake with the wrong answer. And we know that 0.8 and 0.3 were right, or at least we assume they're right based on our work, which could have been wrong also, I guess. But hypothetically, if we made a miscalculation somewhere along the way here, and we use 0.854 and it's wrong, then we'll get a wrong theta as well. So I'm going to use my measurements of Rx and Ry. So in reality here, what we get is we see that the tangent of theta is opposite over adjacent. You want to come back, Nick? You want to help us and say, how do I find out theta now?
So if it's opposite or adjacent, then...
How do I get rid of the tangent, remember?
Yeah, so you need to do... It's like
You got it.
a 10.
What does it look like? Just tell me what it looks like. That's all right.
I remember doing the calculator somewhere.
Yeah, it's in the calculator for sure. Inverse tangent is the word. That's the word you're looking for.
Yeah, exactly. Yeah.
And this is literally, guys, why you did this in your summer packet. This is the reason I had you do it in the summer, so when we get to this point, it's familiar. Maybe the word isn't there, no big deal. Inverse tangent is the word, by the way, but it's not a big deal as long as you know how to calculate it, right? You know how to write it correctly. So what do we get as an value for theta here? I think if I did this, did it ahead of time. Unless someone's got it for me. What do you got?
56 degrees.
Yeah, that sounds about right. Now, by the way, this is one of the first tests where if you don't have a calculator in the right mode, you're going to get a lot of wrong answers. A lot of wrong answers on this test. Next test. Okay, so keep in mind that when you hit mode on your calculator, it should say degree highlighted instead of radian. Is that what you're going to ask?
Yeah.
Hit the button mode, and if radian is highlighted, go over to degree and enter on degree, because we are measuring angles in degrees. That's why. Now, the last step for today, the last step that we really need to consider is that we need to write this as one final statement. So, from your starting point to your ending point, is this person, Joe Schmo here, sorry, we need something just like that. Joe Bob, Joe Schmo, so whoever this person is, does this person walk north, south, east, and or west from beginning to end, displacement-wise? I don't care about the path taken, displacement-wise. Which way does this person physically move there?
Southeast.
Southeast. And if you don't see it, physically look. You're here, go south, go east. You're at your ending point. Or go east and go south. That's fine also. Because our angle, theta, is always with respect to the horizontal axis, we say south of east. Because what is east to you guys? Right now, east would be going that way, right? South of east would be below it. Literally, east is directly that way. That is what south of east means. So if you ever heard east of south, that's the opposite actually. East of south would be starting going south, and then your angle will be measured this way, east of the south line. But we are going to say southeast because it's south of the east line. So in this problem, our answer can be written as 0.854 miles, same units I had, at 20.56 degrees southeast. And again, southeast physically means that you are moving south of the east line. South of the east line. And that's where angle theta in this case is measured. Here's the east line, and we moved south of that. And that's our direct line from A to B. So a lot of work, right? A lot of work for one problem. I mean, we spent 22 minutes just now on that, by the way. 22 minutes. But I'm breaking it into every little piece, which as you get better at this, you will not have to do regularly, right? You will not have to do this on your own all the time. What I want you to do tonight, how much time do we have? Just so I know.
1 minute.
1 minute? Okay. What I want you to do tonight is the following. Listen carefully. I want you to, on your iPad, get an aerial view of Google Maps in Manhattan. So go to Google Maps, just look at Manhattan from a perspective. Screenshot it. Bring it into Notability. Start somewhere in the city and end up somewhere else where you have to move diagonally. And figure out your overall displacement and angle. So let's say, for example, start at 87th and Lex, right? And go to maybe 65th and Madison. Or 95th and First and the west side of the city, whatever you would do. And mark out the path you would have to walk. Focus. Mark out the path you would have to walk, but I want you to find the overall displacement from beginning to end. That's what I want you to practice tonight. You don't have to break it over to this tonight, but I want to see that submitted tonight. Okay, again, Google Maps, walk somewhere diagonally, show the path you can walk along, like down the avenue, over the streets, but also show me the resulting vector. Don't forget your project deadline is coming up soon.
Oh, that's amazing.
Yeah, absolutely. Absolutely. It's a shorter text. It doesn't work that way. You never get that.
So Google Maps show where you outside the city. So what's the, this is on route, right? So you gotta
Which one is adjacent and hypotenuse?
Cosine.
Cosine, I agree. So my ratio would say the following. I'd say the cosine, right, of the angle, which what is the angle measurement here? Yep. Equals adjacent. Yeah, there you go. Okay? So that's my ratio of that. And how would I solve for x? What would I do to finish it off? How do I get x by itself? How do I get rid of the division by 7?
You times the cosine.
Yeah, multiply both by 7. 7's cancel on the right. And that's the value of x right there. So the horizontal component becomes whatever the vector length is, right here, times the cosine of this angle. What if I wanted to get somebody else help me out for the vertical component? Let's call that y. Let's say we wanted to get the vertical component as well. How would I figure that piece out? Right off your summer packet. We should all be, hands should be through the roof at this point if we did that summer packet. It's review, 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 review. Chinmay, help us out. Do it.
Sine 45 equal to y by 7.
Well done, sir. And then solve for y, Chinmay. Go ahead.
And then you have to solve for y. So it is 7 sine 45.
Exactly. 7 sine 45. Good job. Multiply both sides by 7 again, as we just did a minute ago, and we'll see that cancellation. So this is our representation for the y value. So can we make some sort of a generalization? Can we make a generalization? What can we say about the horizontal and vertical components in general? If I change 7 to another number, what's going to change, really? What's the only thing that changes is this, right? If I change the angle to another number than 45, that's all that changes is here, right? So give me a general rule. Yeah.
They're like the same.
Yeah, they're pretty much the same. What's the one thing that's changing is?
The coefficient. Or,
The trig ratio.
Yeah.
Trig ratio. Now, in your calculator, if you do this, it turns out you're going to get the same answer when it's 45. Because when you kick a ball at 45 degrees or when a vector is at 45 degrees, it means that the horizontal and the vertical component are the same, actually. They're the same value. So these are the same values, actually. But if we change that value of 45 to say something less than 45, like 30, try 7 cos 30. Let's make this 30 degrees. Try 7 cos 30 and 7 sine 30. What do you get for those? Good point there, Izzy, that those are the same values. So let's set this angle and we'll call it 30 degrees. I did not measure it, but we'll assume for now that maybe it is just 30 degrees. Okay, so this is 30. Let's go ahead and take the length of 7, that same length, and multiply it by cosine 30. What does that come out to be for the x component? Come on, people, calculators, take them out. You should have your calculators out in class. If I ask a calculation and no one raises a hand, it means you're not paying attention and focused. Izzy?
Wait, this is sine?
Either one.
Sine 3.5.
Okay, and Helen, go ahead. What was the other one you said?
Sine 45 times 7.
Sine 30 we're going to do now.
Okay.
Yeah, we're going to change it because what Izzy picked up on is that these two values are the same. So if we figure out what they are, that's fine, but I want to see the difference when the angle's a little bit lower.
Yeah, we'll put it.
So we have 7 cosine 30,
You're doing that.
7 cosine 30.
Okay.
6.06. And 3.5 for the vertical. I'm taking everyone's word on that, right? Try again 7 times the sine of 30 right there. So the half of 7 should be 3.5. So what you're noticing is that the x component is greater than the y component again. Why? Because this angle is less than 45. So the generalization that we're noticing here is that we can always take this rule. So let's write an actual rule for that. Yeah. Let's physically write a rule for this. So if we have a given vector, let's call that vector r, at an angle theta, we could say that the rx component, which is this, is going to equal whatever r is times the cosine of theta. And the ry component, which is this, is going to equal whatever the vector is times the sine of theta. The idea is that I don't want you to have to derive a triangle every single time you work in this class. And in the next section, we're soon going to start projectile motion. We're going to talk about what if the velocity of an object is not horizontal, not vertical, but both. What if an object is kicked or launched at an angle, or thrown, or whatever it is, at an angle? Well, we have to break it into its components to get the x velocity and the y velocity separately. So instead of r, we're going to call it v. V for velocity. Okay? It's the same exact formula, though. So if you want to, go ahead, look at your formula sheet, and you should see this on it. It should be familiar now. Okay, this is right on your formula sheet, top left or right. It's in one of the top corners on there. Now, what's the other thing we could write? There's one more piece here. If we wanted to figure out the angle theta, and a lot of the time when we work with vectors, we're going to have these components and not necessarily have the r. So using rx and ry, what ratio would I write to figure out theta? Using rx, look at the triangle, using rx and ry, what trig ratio do I have to use to figure out what theta is?
Rx squared plus ry squared equals r squared.
That'll give us the length of the vector, but how do I figure out theta was the question? Theta, right? The angle is what we're looking for. How would I figure out the angle? Good?
Tangent.
Of?
Inverse tangent. So.
Let's give me the ratio first. Tan of theta equals?
Whatever r. Oh, my bad. Opposite, so whatever ry is over r.
There it is. Okay, so if we want to figure out the value of theta, we can do the inverse tangent. Guys, this has to be something you know. And we went over it in the summer packet. I asked if you had questions on it. People really didn't ask many questions on it, and no one has seen me for help. And I get dead looks from 75%. It's not a good sign. So if I don't see a lot of hands up for something like this, I know that there's something clearly not happening, right? We need to make sure if we don't get something, we advocate for ourselves. So the actual value of theta is the inverse function. That's always going to happen when you're solving for theta in a right triangle. Whenever you're using a trig ratio to get theta, you're going to use an inverse trig function. It's going to happen every time. So this should be familiar to you by now. It should be familiar to you by now. All right, let's take a look at the same vector addition problem that we had earlier with the graphical approach, but now let's take a look at the algebraic approach itself. So if you recall, this was the original problem we started with. And we broke it into components, and then we added those components together to get the overall result. And we did this graphically, and we showed it, and then we went into that example where the person walks, right? And walks around and kind of result in that. But here, we want to take a look and say, well, where does this AX come from? Where does this AY come from? Like, where do these values come from? And we know where they come from now that we have the last slide that we wrote about that rule. We know that the X component comes from the cosine, and the Y component comes from the sine. So let's focus on this middle diagram for a second. I'm actually going to put it over here so I can have a little bit of room below it. If I want to figure out the AX value, it's the A vector itself. I'll do one example so you can see it. It's the A vector itself, which in this case is 12. It's given at the top. If you don't see it, look up here, please. The A and the B vector length and angle are given. So vector A is 12 in length and an angle of 20 degrees. So this is going to be 12 times the cosine of 20 degrees. I'm using literally what we wrote in the previous slide. So if you're like, where does it come from? Look at your Rx and your Ry value. When it said Rx, we took R times cosine theta. So we're taking A, which is 12, times cosine of its angle, which is 20. How do I get the AY value? Step me through it. How do I get the AY value based on the AX? What's the one thing that changes? Izzy said it a little while ago. What's the one thing that changes for AY? Go ahead, Izzy.
Maybe 4 sine 20.
It's definitely sine 20. Where's the 4 coming from now? Don't look at the diagram. Remember, look at the length of vector A, which is up here. Look up here. See where I'm circling? Up there at the top.
Oh, so it would be 12 sine.
Yeah. That's all right. So you saw the diagram and it kind of misled you. You saw this 4 over here. That's the result we're going to get. So let's go ahead and calculate these numbers, please. Go ahead and check them yourself. I want you to physically practice it so I know that we're actually guaranteeing that they're going to use their calculator, right? I can't tell you how disappointed I am on the last steps. I really am. A lot of them small errors, and like right now I'm seeing reasons for small errors. People don't focus and people don't practice things. So many miscalculations, it was unreal. I had to dock half point every time. People lost like 3 points out of 50. That's 6% of your test on miscalculations, left and right. We need to be practicing in class. And if I have to be mean about it, I will be mean. I will start giving zeros for classwork when we don't have calculators. It gets annoying when I don't see the production on the test. If I saw the production, I would be fine. But I'm seeing small mistakes adding up on a lot of tests. What do I get for these values? Go ahead.
For AX, you get 11.3. For AY, you get 4.1.
And if you didn't even notice it, look at the diagram now and look at the correlation. Again, this AX is the piece of this triangle that's the length in the X direction, and it's less than 12 because the hypotenuse was 12. So these answers are reasonable. It's a low angle, so AX should be much bigger than AY, and it is. It's much bigger than AY. Do the same thing for B on your own. Verify these values here.
So we'll why would you use the sign for the AY instead of the cosine?
So if you recall, if you go back to the previous slide, look at the ratio that we used.
Yeah.
So for this value here, you gotta have this stuff written down.
Okay.
If we're looking for the actual RY value, it becomes, in this case, the opposite of the hypotenuse.
Yeah.
And which trig function is opposite of hypotenuse?
Yeah.
It's sine.
Yeah.
So when we're doing the Y value, that's where it comes from. And then the cosine comes from the X component when we do adjacent of hypotenuse.
Okay, thanks.
Okay? Again, though, you can memorize this at this point, but you don't have to. It's on your formula sheet. Look at your formula sheet if you don't believe me. In the corner, you'll see Rx, and it says take the R vector, in this case the A vector, which is 12, times the cosine of its angle, which is 20, and then continue for the B value the same way. Vector length B is 25. When I want the X component, I multiply it by the cosine of its angle, which is 60. The same thing for the sine component here, which is also 60. And I don't even have to ask the answers because I know they're right here, and I know they're right because I see them here. But I want you guys just to verify it for yourself so you understand where these numbers are coming from. It's not just magic. I did a teacher used to say something about mathematicians, where you just make things look like they're right. There's reasons for things here. There are reasons for them. These are the trig ratios. So the 12.5 corresponds to this length. And look at vector B. Vector B is a little bit higher than 45. And the Y component turned out bigger than the X component. Turned out bigger than the X component. Now, again, just like yesterday, with the graphical approach, we said segment addition postulate tells me I can add AX and BX together to get the overall length RX, and that's what's shown here. Take a look at the diagram. You take AX, which is in this case 11 point, we're going to do this in a minute with the problem. Take 11.3, and you add the 12.5 to it, you get 23.8. So this full length here, which is what we're trying to figure out, the goal is to figure out this whole length and this whole length so we can get R, the result of this whole thing. So the sum of these two gives you this value. The sum of these two gives you this value right here. So 4.1 goes in for AY, which is here, plus the BY, which is 21.7, and that equals 25.8. Again, the goal of these problems is to figure out if the person or if an object went straight from A to B, or from beginning to end, and didn't take this weird route, what would that length be? And that's what we're doing to figure it out. Our goal is to figure out the resultant, which is called R. We will use this when we're putting together velocity. If we have an X velocity and a Y velocity, we can put it back together into one velocity at the end. Okay, it's going to be used as components of velocity, but you have to understand the math to do it. But again, I want you to see where you're going with it. You kick a ball, it goes in both the X and the Y, means you're giving both kinds of velocity. So in that problem, you would have VI in the X, and you would have VI in the Y. And they would be different values if the angles are not 45. If they're 45, they turn out to be the same. It's the only time, because 45 is halfway to 0 to 90. Would you hand it a second? Sorry.
So the 20 degrees is at what angle again?
The 20 degrees is this guy right here,
Yeah.
and then the 60 degrees is this guy right here.
Oh.
Okay? So it's the angle that they make with their horizontal. So again, the angle that A is rated at is up here at the top. It says 20, and that's going to be this little red arc I'll put right here. Can you see that little red arc I kind of drew right there? It's buried there. And then the blue arc is a little more obvious. Okay? Take a look at the difference. This is a 60-degree angle, right? We can see that the opening is physically greater in this case, whereas here, a 20-degree angle. We have more of a narrow view, right? Okay, so those are the differences. And that's where these angles come from here and here for A and B. Remember, all this work is pertaining to this graph here. Okay, and then we added it together over here on the side to show the full lengths. So I want to practice this with an example, and I need you to think. Imagine if you were crossing Central Park. That's why I had you guys do that optional activity with the Angry Birds or Google Maps. And the idea of Google Maps was something because every year I do this thing where you say, what if you're crossing Central Park? You really can't ever cross correctly, right? Would you agree with that statement? You really can't. And if you take even a curved path, you can break any curved path into segments if you try hard enough. So if I were to walk through Central Park like this, and then turn for a while, and then continue maybe at another exit, I could think of that as a line, and a line. Would that be reasonable to estimate? And I can think about those at angles. Those lines are not necessarily going to be perfectly north. So if it's at an angle, I have to break how far did I go on the X, and how far did I go on the Y rate. And we'll do that with these diagrams again with an example. Okay, so let's jump in. Look at this example now. So again, in this example, we're going to have to draw a picture of what's going on. And we're going to have to try to visualize it. Now, you're not going to be able to draw it to scale every time, but try to be reasonable with your lengths. If this is 5 meters, and then you go to draw 10 meters, it should be double this length, right? So if your 5 meter length and your 10 meter length look the same, then your figure is not even close to scale. If it's an angle of 20 degrees, okay, and if you make your angle like this, that's like an 80-degree angle. That's 45 right there in the middle, right? That's 90 right there. So try to make things somewhat close to scale so you can physically see it, because we don't have a grid line anymore, so we have to kind of just estimate. So John starts at the southwest corner of Central Park. So let's put him down here at the southwest corner. Right? South is down, west is left. So we'll put him at the southwest corner there. And we're told that he walks at an angle of 30 degrees northeast. First of all, what did we talk about yesterday? What does northeast really mean? What does it really mean, Panatcha? North of east. So where's east? Yeah, so draw a dashed line for east so we can see that, please. Right, that's east right there. So northeast physically means north of east. So I start at east and I go 20 degrees north of that. So that's the angle that we're referring to. If it said 20 degrees southeast, we go south of east like that. We're never going to be doing east of north or east of south. That would be like, if it said 20 degrees east of north, you start at north, you go 20 degrees east from there. But again, ours does not say east-north, it says northeast. It's important that we recognize that those are different things. So 20 degrees is like this. Okay, and this is 0.8 kilometers. And that's 20 degrees. And again, that might not be perfect. Let's see how close I am to the diagram. I don't think it's actually going to be good. Let's see. Yeah, mine is about 27 degrees. So mine's definitely too big.
It's 30. It's yours is right.
Thank you. 30. Oh, so that was lucky. That was lucky. That was not on purpose. Not on purpose. So 30 degrees, thank you. Now, the next part of the trip says that he then stops. He eats lunch and enjoys the wonderful weather. And enjoys the wonderful weather before heading 25 degrees southeast. Southeast. But remember, it's southeast from this point. So what do we have to draw again? We want to go southeast from this point, not from here. So if I'm at this point, what would help me? What should I probably draw that I drew earlier? Another dashed reference line. So let's go ahead at our next location and draw another dashed line. Remember, these dashed lines are not vectors. They're just reference lines. So if I were to then walk east from where I ended, it would be along the dashed line. But we're not walking east. We're walking southeast. And it's 25 degrees southeast. So southeast is south of east. So our next vector is going to look like this instead. And it's going to be at a 25-degree angle, and it's 0.5 kilometers. So I know that it should be less than the 0.8. Is that agreeable, right? Less than the 0.8? So we can do this and stop right there maybe. And that's going to be 0.5 kilometers. And again, at 25 degrees southeast. And our goal in this problem is to figure out his overall displacement. And when you hear displacement, displacement is a vector that we talked about. So when you hear a question that says find the displacement, it means find the length overall and the overall angle. So let's connect starting to ending. Use another color to see that, please. Connect starting to ending. I'm going to use yellow for here. So the yellow vector that you're seeing is my, remember, resultant vector. That's what we are trying to figure out the length of and the angle of. Now, what angle am I referring to when I say the angle for vector r? What angle is it?
30.
No, it's not 30. Be careful. Careful. Remember, vector r is in yellow. What angle am I talking about? The angle between that vector and what? I said it yesterday. Think back. Whenever we're looking at the resultant angle, it's the angle between the vector itself and the horizontal line. Very good. So it's this little angle right here. Take a look. Right here, that little angle. So it's going to be something probably pretty low. Okay? It's probably not going to be negative. It's going to be positive. It looks like based on my diagram. But again, my diagram is not drawn to scale. So I don't know. Maybe this vector of 5 or 0.5 goes down below the horizontal. It's possible. Who knows? Maybe it does. And therefore, my final answer will be southeast. But it looks like my final answer is going to be northeast. It looks like it. But let's figure it out. So we have to do what we said before. We have to break everything into components. So before I actually show you the table, let's visualize this. Let's draw our triangles. So here is the height of the first triangle, and here is the width of the first one. So let's draw on those little right angles right there. Okay? So my first one we'll call A, vector A. So this is like AY right here. And this red part here is AX. That's my first vector. Again, I'm not worried about my resultant, because the resultant we'll take a look at the end. My second vector, let's use blue. Here's the horizontal component of the second vector, and here's the vertical component. And remember, my subscripts are just indicating whether it's horizontal or vertical, each piece. Now, AY goes up, and AX goes right. Up is positive, right is positive. Agreed? Up is positive, right is positive. So look at the red path, please. Positive up, positive right. But the blue path, Lucy, is
Positive
and then negative. So BY is a negative value. And we're going to talk about how we approach that in this section now that we're doing it algebraically and not just graphically. So let's go ahead and make the table that I was referring to. I have the table actually written. I forget how I want to be consistent with the way I'm going to give it to you. I did last year. Let's see if it's the same way. You can go ahead and draw a table with at least 3 rows and about 5 columns. 3 rows and about 5 columns. You can start making a table for. One sec, Thomas. Hold on. Come on, why is this table not loading? I've actually used 2 different methods to do this. That's why I'm just checking to make sure that I'm consistent with my notes from last year. Okay. So what I've done is this. I start by making an X row and a Y row. Okay? Start with an X row and a Y row. I then, along the top, label the actual components themselves. So in this case, I'm going to talk about the A vector and the B vector, and then the resultant vector. So if I want the A sub X component, meaning this right here in red, it's going to go in this box. It's going to go in this box right here. The height AY is going to go in this box. The reason I'm doing this is because then once you get a number here and a number here, we'll see that we can add them up to get R. And then we'll add these 2 boxes to get R. But let's talk about this again. How do I get AX? What would AX be? And remember, the standard form is that RX is R cos theta and RY is R sine theta. That's my standard thing to remember that's on your formula sheet. So what would I write for AX in this first box here? Use the formula that you're seeing in the top right. What's the actual length of A? Just read it off the pie. Yep. 0.8. And what's the angle that A is at? 30 degrees. So I say cosine 30 degrees. And again, it's the same process as earlier. The length of the vector is 0.8 times the cosine of the angle. That will give me this AX component. The sine is used for the Y component. So you repeat the same thing, always. It's always the same thing below, except instead of cosine, you write sine. Since, as Lucy told us, both of these directionals are positive, it goes up and then right, I leave them both as positive. Take a minute to let that sink in, right? Let that sink into your brain, make sense of it. These are both positive here. Cosine is associated to x, sine is associated to y. Part B, write it out yourself. Take a guess and see what you got. Write it out yourself for here and here, considering that B is a different angle and a different length, and part of B is up, and part of B is down, or part of B is right, and part of B is left. Try to fill in the B column yourself. Try to fill in the B column yourself here. Check your work. What do I have to add to this? What do I have not included yet? There's one thing I haven't included.
You need a negative
For which one?
for y.
Yes. That's the key here. The BY value, look at my diagram. Since I'm moving southeast, east is positive for the x direction, but south means negative for the y direction because I'm coming down. And what we said earlier was this. Take a look at the diagram one more time. I'm going to do it. Hopefully he gets when he gets back. This right here, remember, is Rx. And this little piece right here, from beginning to end, is Ry. Because again, what's the R triangle look like? Here's the R triangle in green. It's a very, 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 very low angle triangle. Again, R is this vector length here. This is the base of the triangle. This is the height right here. So if I add AX and BX together, I should get RX. Is that visible to see that here? Again, segment addition, add this and this, you get the whole thing. So if I want Rx, just add these two together and get a number. Again, this piece plus this piece equals the whole thing. This is piece A, this is piece B, this is the whole thing. That's going to go right here.
Is that little segment RY?
RY. This is a little tiny height right there, yep. Take R, which is yellow. See my yellow vector is R? And think about making a triangle out of it. The height of that triangle is going to be very low because this is a very low angle. Right? Think about this angle. It's a really small angle. So this RY value is going to be very short. A very low angle makes the base very long. So again, we're going to sum together across the rows. So what goes in here is going to be whatever value you get. I don't know specifically what number it is, but let's add this to this to give me Rx. Again, adding these two gives me the total. Let's figure out what Rx turns out to be there. And you can type this all in your calculator in one line. That's the best part. You don't have to do this twice. Type it in like this. 0.8 cos 30, close your parentheses, plus 0.5 cos 25. You can do it all in one line, just put the answer right there. You don't have to get each of these individually if you don't want to. So again, type this all in one line with a plus sign in the middle, and put it there. And then here you're going to do this plus a negative, or just minus in that case. So in my notes, I don't use the table method. I use that other method I was telling you, where I draw on all the lengths and then I just write x components and y components. So if you don't like tables, there's another way you can approach this as well. But I think in the past, students have done better with the table method here. So what do I get for Rx as a number?
1.15.
Yep. Check your math. Make sure you got 1.15. Again, adding these two together, giving you this. For the second part, yeah.
Oh, wait, no.
Okay. For the second part, we have to recognize that yes, 1 is negative. So you could just take this number and subtract this from it. Or do plus a negative. It's the same thing. The definition of subtraction is adding a negative. So we've got 0.8 times sine of 30 plus negative 0.5 sine 25. And what is that going to yield in this spot right over here? Luce?
0.187.
So if I'm rounding, I'll do 1.9. That works. And recognize that that does make sense. It should be very small. Look at your diagram. Look at your diagram in green. Ry is quite small. Rx is quite large. Look at the difference in the actual values. This is 5 times as big as this one. More than 5 times. So we recognize that we've got the components of the R triangle. So on the right, if you're done with this, and when we're done with this problem, I like to do this sometimes. I draw my R vector, and I rewrite what the dimensions are. So this is 1.15, and this is 0.19. That's my angle theta right there. So all I've done is taken my triangle in yellow and green down here at the bottom, and I've kind of extracted it over to the right. And again, the 1.15 is the x length of R, the 0.19 is the height. We need to figure out the angle theta and R. R is the easy one. R is the easy one. Everybody gets that right. What do you do to get R?
Oh, the angle stand.
Angle stands. Yeah, that's the hard part. Pythagorean theorem, right? You do the hard part. The hard part is the tangent. Well, not hard part, but that's the part that people seem to have trouble with. So to find the actual length of R, we can use Pythagorean theorem. 1.15 squared plus 0.19 squared equals R squared. Sum them, take the square root. R will be 1.17. And remember, this length has to be larger than the sides that I had to start. And it is. Okay, the sides we had to start was 115, 0.19, and 117 is bigger than 115. So it's reasonable as an answer. And then if you recall, as Thomas said here, if we're looking for theta, we have opposite and adjacent. Opposite and adjacent. So we can do the tangent of theta equals 0.19 over 1.15. Solve for theta by doing the tangent inverse of that ratio. And you'll get the actual angle measurement on the right. Check your work. You should get 9.4 degrees. So what this means is that this person took this trip along the black path shown, but instead, he, John, could have taken this trip directly along the yellow line by following a length of 1.17 at an angle, or a bearing, if you have to vote, it's a bearing of 9.4 degrees. Okay, a bearing off the horizontal itself. Okay, so it's 1.17 kilometers at 9.4 degrees. What is it? Northeast, southeast? What is it? From beginning to end, does this person move northeast, southeast, northwest, southwest? Which way?
He's going east.
East for sure. Look at the green triangle. Yeah, because you go east, right, and then north. See how it works?
Oh yeah.
And look at your sign. Aren't these both positive?
Yeah.
That means we go to the right, and then we go up. If this were, take a look up here where I'm pointing, please. If this were positive, it means you go east. If it were negative, it means you go west. If this is positive, it means you go north. If this is negative, it means you're south. Since they're both positive, it means it's east and north, so northeast is what we're looking at. And that's my final answer for this last part. Yeah.
What is the symbol between 1.1?
At. An at symbol. Now, something to point out. Something to point out. What if John, ready? Take a look, please. What if John, at the end of this trip, instead of stopping, went a little bit further east? And watch the diagram, please, where I'm going to point. What if John instead went like this? Take a look here. Went east afterward. How would that show up for my third, so A, B, this would be vector C now, right? How would this show up in the table? If he's only going east in the third vector. What do we not have to worry about in that case then?
You don't have to go to X, Y. Or you don't have to go to Y.
Yeah, just one of the components. Think about this. If John only goes east, east and west is the X column, isn't it? Or the X row. So what would go in this, if I were to add a little, don't put this in your notes to confuse you right now, but I want you to see it, just visualize. C would be here. There would be some number here, right? Say he walks 5 miles east. That's what that number would be. But what would I put for the Y component? I would put 0. If ever part of the track is only east or only west, that only goes in the X slot. If the person only goes north 3 miles, this would be a 3 right here. And then this would be 0. Because this is east to west, and this is north to south. So whenever the person doesn't go at an angle, but goes directly east, or directly west, or directly north, or directly south, we're going to have a 0 in one of these spots for sure. Okay, we'll have a 0 there. Now listen, it was 20 minutes we did for that problem. 20 minutes just explaining it. So when you have homework tonight and you're working through this, if it takes you 10 minutes on your own or 15 minutes without stopping and talking, that's normal. That's okay. It's not the end of the world.